Okay, so I want to get back to the spin statistics theorem, and the main thing that we're going to use besides Lorentz invariance is causality. Now, most of the books, they sort of just give a very simple argument for causality, and it sort of goes like this. Basically, here's a space-time diagram. Let's say here's a point x, and here's a point x prime. Here's the light cone. Now we know that, x prime. We know that if x and x prime are outside of each other's light cone, in other words, it's space-like, that what we do here shouldn't be able to affect what we do there, and vice versa. That's what's known as causality. And so they say that relativity demands that nothing here affects nothing here. A measurement of a field here shouldn't affect the measurement of the field there. Let's call it phi x prime. And you might remember from quantum mechanics that you can measure two things independently. One won't affect the other if they commute. So they then just go the commutator of phi of x, comma phi of x prime equals 0 when it's space-like. And this is a little bit of a hand-waving argument because, in fact, if you were to calculate the propagator to go from here, this point, to this point, you would find it non-zero. It decreases exponentially outside of the light cone, but it is not zero. Nevertheless, this is true. And Sernetke gives an alternative derivation and reasoning of why that's true. By the way, if the points are in each other's light cone, like x double prime, x triple prime, then of course there's this will affect that and the commutators won't vanish. But we're mostly concerned when they're outside of each other's light cone. And not only that, in a different reference frame, we can draw the boosted axis might be like this. So in the original frame, this occurs, x occurs before x prime, but in another reference frame, x prime occurs before x. So let me start by giving what our author in the textbook does. And the first thing he does is he writes down a formula, which hopefully most of you will have seen, but if not, it will be, it's in quantum mechanics textbooks, and I think we might derive it later in this course, and it's basically the fundamental formula of time-dependent perturbation theorem. Notice I said time-dependent, not time-independent. Time-independent is much easier. But this basically says that the probability amplitude for a transition from state I to state F is given by this formula. F, this is like a squiggly T. F, time order operator, I'll explain that in a second, times the exponential minus I, the integral from minus infinity to infinity, dt h I t and I. So what does this formula say? It basically says if we start in state I, we'll end up in state F after we apply these operators, and this operator is what is known as the, this is a perturbation Hamiltonian, and this is like in the interaction picture. Now, online I'm going to post a one-page sheet from my book which describes the interaction picture, the Schrodinger picture, and the Heisenberg picture. We don't really need to know that for now. I think, by the way, this should be a 1. Maybe it's an I don't know. Anyway, when we want to get an interaction Hamiltonian, we use the free particle Hamiltonian to bring it into like the Heisenberg picture. Yeah, this is definitely a 1, I think. But I'm not sure the notation used in the book. So this is usually how we get interaction picture operators. We take the Schrodinger operator, which is time independent, and then do this evolution using the free particles Hamiltonian, or the free Hamiltonian, and we get the interaction Hamiltonian. The important thing here is this time-ordered operating. The operators here are all designed so that if, let's say you have h of t1, h of t2, if t1 is less than t2, then this is equal to h of t2, h of t1. And if t1 is greater than t2, it's the opposite. So the latest operators go on the left. And this is the argument that Srednicki makes. He says, this formula will only be time invariant if it has to be the same formula in all reference frames. Now, when we're in the light cone, when we're like here and here, it doesn't matter because in every Lorentz reference frame, this operator will be first and this operator will be second. But if we have operators that are outside the light cone, then in one reference frame, as I mentioned there, this one occurs second, but in the other reference frame, this one occurs second. So we're going to get, in one reference frame, we're going to get this. In the other reference frame, we're going to get that. And the only way we're going to get the same result is if these operators commute. So this implies that we have to have this commutator between the Hamiltonians has to be equal to 0 when we're space-like. So that's the same conclusion we reached over here because these interaction Hamiltonians are going to be functions of the fields. They're going to be, some kind of functions of the phi pluses and the phi minuses. And so we're going to get the same conclusion there. We're going to have the fields commute. Actually, what Srednicki shows, and I'm not going to show it, is that he shows that the fields, if you define linear combinations of the fields, you can satisfy this, but you're going to end up getting back to just a phase difference, and you're going to get back to where you were. So, and then he makes the point that if we use anti-commutators for fields, we're going to get something like this. If we use anti-commutators, this is going to be equal to like 2 phi x squared. So we're going to get a very trivial theory if we use anti-commutators for the scalar fields. And I left out one thing in my argument here, that what Srednicki shows in the book, and it's the first exercise, and I'll have a little very brief video on it, that phi plus x, comma phi minus x, this commutator is equal to m 4 pi squared, some modified Bessel function. Your guess is as good as mine when it comes to modified Bessel functions, but it's not 0. So the only way in which we can make it 0 is if we take a linear combination of these things, and we end up getting, the linear combination ends up being phi plus phi minus, which is equal to phi. So we end up getting back to our scalar fields, and the idea is simply that we can't just use creation operators, we can't just use annihilation operators, we have to use fields. And Weinberg makes this point really effectively, that we always end up with fields. So this is a brief chapter. As I said, the main thing is you just remember fermions, half-integral spin, anti-commutators, bosons, integral spin, commutators. The next lesson will be on the Kalin-Lehman reduction, I believe. And it will be on the LSZ reduction formula, and that will be very important for everything we do in quantum field theory. So I'll see you next time. Thank you very much. Bye-bye.